Hello everyone, today in this video we are going to talk about force between two current carrying conductor, and after this video you should be able to derive the expression of the force between two conductors and define 1 ampere using the expression of the force. So from Oersted experiment we know that a current carrying conductor produces magnetic field. And from this activity we know when we keep a conductor in a magnetic field it experiences a force. So if you combine these two, we can say a current carrying conductor exerts force on other current carrying conductor. And this demonstration was shown by Ampere, and he took a circuit. Two conductor is dipped in mercury, and when the circuit is switched on the current flows in different direction, and he found that the conductor repelled each other. And in next experiment he sent the current through the conductor in the same direction, and he found that the conductor attracted each other. Now we know a current carrying conductor produces a magnetic field which are concentric circles around it, and the direction is given by right hand thumb rule. And if you give the direction to the magnetic field, so from this side the magnetic field is coming out of the screen, and from this side the magnetic field is going into the screen. So we can just represent a magnetic field of a current carrying conductor by a dot and cross. So now let's take one conductor. And current is flowing in upward direction. So using right hand thumb rule I can draw the magnetic field. So if you keep another current carrying conductor which is having the current in upward direction and magnetic field is going into the plane of the screen, so there will be a force which is towards the left. And similarly, if you consider the magnetic field of this conductor using right hand thumb rule, so out here the current will be coming out of the screen. So for this conductor current is going upward, magnetic field is coming out of the screen, so there will be a force towards the right. So two current carrying conductor in which current flows in the same direction, they attract each other. Let's take another conductor, the magnetic field, using right hand thumb rule. So now I am considering another conductor which is taking the current in downward direction. So I will use the Fleming's left hand rule again. Current is going in downward direction, magnetic field is going into the plane of the screen, and the force will be towards the right. So now if you consider the magnetic field of this conductor using right hand thumb rule, so in this side the magnetic field will go into the screen, and from this side it will come out of the screen. So for this conductor magnetic field is going into the screen, current is going upward, so force is towards the left, so it will go away from this conductor. So for two conductor taking the current in opposite direction, they repel each other. So now let's derive the expression of this force. So I am considering two conductor having current I1 and I2, and the distance between them is R. So I am drawing the magnetic field line of this conductor number 1. So this side the magnetic field is coming out of the screen, and for this side magnetic field is going into the plane of the screen. So for this conductor magnetic field is going inside, so the force will be in the direction towards the left. So now I have taken the same thing. Now F2 is the force on the conductor number 2. We know from our previous video the magnetic field due to an infinitely long conductor is mu naught I by 2 pi r. So magnetic field due to this conductor number 1 at this point, that is B1, can be written as B1 is equal to mu naught I1 by 2 pi r, and we are keeping the conductor number 2 in the magnetic field of conductor number 1. So direction of magnetic field is given by right hand thumb rule. So out here magnetic field is going into the plane of the screen. So now the magnetic force on this conductor can be written as BIL sin theta. B is magnetic field due to conductor number 1, and I is current flowing through conductor number 2, L is the length, and the angle between magnetic field and this current is 90 degree, because magnetic field is going into the screen and current is going upwards 90 degree. So I can write F2 is equal to B1 I2 L. So if you put the value of B1, that is mu naught I by 2 pi r, then you will get force 2 will be mu naught I1 I2 L by 2 pi r, and using Fleming's left hand rule the force is towards the left. Similarly, we can find the force on conductor number 1 due to the magnetic field of conductor number 2. So only the direction will be different, other values will be same. So now these two forces F1 and F2 brings the conductor closer, and the force per unit length can be written as small f is equal to force by length, and this is the force because F1 and F2 are equal, so I can take any values, so by L. So I can cancel L and L, so I'll write F is equal to mu naught I1 I2 by 2 pi r. So this is the expression of force per unit length between two conductors, and the nature of force depends on the direction of the current. If the current is in same direction, they attract each other. If the direction of current are opposite, they repel each other. So now let's define 1 ampere using the expression of force, that is mu naught I1 I2 by 2 pi r. So if you take I1 is equal to I2 is equal to 1 ampere, and if you take distance between the conductor to be 1 meter, then we know the value of mu naught is 4 pi into 10 to the power minus 7 Tesla meter per ampere. Tesla is the unit of magnetic field. Now if you put the values, you will get force is equal to 2 into 10 to the power minus 7 Newton per meter. So meaning if you take two conductors at a distance 1 meter apart, and if you send 1 ampere current through both the conductor, then the force between them will be 2 into 10 to the power minus 7 Newton per meter, and this force depends on the direction of current. So if they are in same direction, they attract each other, and if they are in opposite direction, they repel with each other with this force. Thank you. Don't forget to like the video.